Oh, did you get something weird? Like a weird guy? Oh, okay. I'm still kind of data, and I don't know what's going on. So, right? That might be the one that's still going on, right? Okay. I don't agree. No, this is John Coleman. I'm a specialist. I don't know. We don't know. The builders and I Gibson. Right down. Oh, you just yep. Yeah. Oh, you could. Oh, maybe I was assuming with you. Is that the one you're talking about? Oh, okay. Yeah, you told me that exactly. You go, oh, they're happy with that egg. Pretty much on that, you know. You know what happened to you? They're happy. I'm like, oh, okay. You can watch that. Really? Oh, really? Yeah. Kind of the way some of you guys, you Ray and Scott, you want to come back here. I'm sorry? I'm not sure. seeing you.
Hello, you've reached my voicemail. Please
Well, that's
leave me a
not good.
message and I'll get back to you as soon as I can. Thank you.
Garth, you trying to call me? Garth, are you trying to call me?
How do we say, John, go ahead.
Hello, can you hear me now? Hello? Garth, can you hear me? Hello?
Hello?
Hello, can you hear me?
Very, very low.
Very low. Let me turn up my microphone. Hello, can you hear me now?
Yes.
Testing 1, 2, 3. Can you hear me now?
Oh,
Uh-oh, volume problems again.
Are we there yet?
somebody look at his phone and call in.
Yeah, I can barely hear you, but it's coming through the computer again.
I can hear you.
Okay.
Anybody else hear him?
Yeah, I think I've got one remote user hearing me. Anybody else hear me? John, we're ready. Okay.
That's Skype. I think you're gone. No, that's the join me.
I can hear you, Garth.
Yeah, we had it running before.
Garth, can you hear me at all? This is not good.
Yeah, this is Osvaldo. You loud and clear.
Okay, and where are you located?
In Connecticut.
Okay. You're not at the dinner, though?
No.
Okay.
Oh.
Garth?
Yes, can you hear me?
I can, loud and clear.
Excellent. You're loud and clear as well. You want to start?
I think we ought to get this show on the road.
Yes, because they're talking about something about another goddamn UConn basketball game tonight.
Oh, yeah. Go Syracuse. Oh, I'm sorry. Okay. Good evening, everybody. I'm assuming you can hear me loud and clear. I'm going to mute everybody so I don't get any feedback. So I'll just ramble on and we'll start this show. Okay, thank you very much for allowing us to push the technology envelope tonight. I know we had a pretty good go at this up for the Minnesota conference and the Wisconsin conference, so we thought we'd try it again. And it's a couple of subjects that I presented at our dealer meeting in Central New York back in February. So I thought I'd share some of these with you tonight. And the main topic, called the Great Hydronic Heist, is about the way we pipe our hydronic heating systems for geothermal. But before I get into that subject, I did want to share one subject with you that I'm calling playing the green card. I can't tell you the number of situations that I've seen go south because of the way the environmental issues were discussed. my own personal experience. I had a doctor come into my office asking me all about geothermal. And I was doing a brain dump, and we were having a great conversation. And then all of a sudden, I decided to interject the perspective about global warming. And lo and behold, I offended him, and he got up and walked out, which amazed me. And then I've had another customer who I happened to ask when I was on the job site. I said, "Did you ever see the movie Inconvenient Truth?" And she grabbed my arm and said, "That's exactly why I'm spending all this money to put a solar PV system in and a geothermal system." So we never know how playing the green card is going to turn out. So my advice is contained here, and putting politics and policy aside, where do you stand on climate change? And I know there's a lot of folks that I talk to day in and day out who do subscribe to the fact that maybe the jury's still out. Maybe it's not man-made. So the question is, do you believe rising CO2 levels are due to man's use of fossil fuels? Now, you can ponder that question, but the point of my presentation is simply your opinion doesn't matter if your true goal is to sell geothermal. You have to know your customer. And at the end of the day, you want to reinforce that your customer is making the buying decision for reasons that are important to them. And my goal today is to at least arm you with some facts, some perspective that you might be able to reinforce their perspective. And as Kermit said, it's not easy being green. One very important aspect of the environmental benefits of geothermal is the so-called carbon footprint. And to give you a benchmark, I'm looking at coal that has a CO2 output per pound of coal of 2.48 pounds. The energy content is 12,250 BTUs. Efficiency could be anywhere, but using a number like 65%, I get a net CO2 output of 311 pounds per million BTUs. Moving on to fuel oil, and of course everybody likes to see one of these in your basement, very sightly. But looking at fuel oil, the CO2 output is 26.4 pounds per gallon of oil. The energy content of oil is 140,000 BTUs per gallon. Efficiency, we'll use 82%. So the net CO2 output is 230 pounds per million BTUs. And then, of course, you could choose to have one of these lawn ornaments near your house. And, of course, it's propane, and we all got put into sticker shock this year, or perhaps we're applauding the spike in propane prices. But the CO2 output for LP is 12.1 pounds per gallon. The energy content is 95,500 BTUs per gallon. Efficiencies could be much higher. It's fundamentally a cleaner fuel, so burning it in a condensing combustion is a good way to stretch efficiency with propane. But the net CO2 output is 135 pounds per million BTUs. And then our most favorite fuel, which is often touted as being environmentally clean, is, of course, natural gas. Now, you all in the East may not be as sensitive to fracking as New York State and other states have become. And perhaps this is a little unfair to illustrate natural gas coming out of your faucet. So we'll go ahead and use a more conventional furnace. And the CO2 output per 100 CCF is 11 pounds. The energy content is 100,000 BTUs. Efficiency could be 92%. So basically, natural gas will emit 120 pounds of CO2 per million BTUs. Now let's look at electric resistance heat. And the key parameter here is how many pounds of CO2 per kilowatt hour. It varies all over the place. If you were to live in Chicago, you're probably close to 2 pounds per kilowatt hour due to the fact that 95% of the electricity is generated with coal. The 0.49 pounds is indeed central New York, which is a fairly clean area of New York. New York State average is 0.76 pounds per kilowatt hour. And I would encourage you to explore your own local generating utility companies to see what their carbon footprint is. The energy content, 3,400 BTUs per kilowatt hour. It's essentially 100%. Every kilowatt hour does indeed turn into 3,412 BTUs. So the net output of an electric resistance heater in central New York is 144 pounds of CO2 per million BTUs. Moving on to geothermal. And again, you've got to calibrate it based on your local electricity generation mix. And certainly in the long term, the grid will get greener. So it will improve over time. Energy content, again, is 3,412 BTUs per kilowatt hour. However, we have an efficiency. A COP of 3.8, we could essentially say it's 380% efficient, and therefore we're going to emit 38 pounds of CO2 per million BTUs. To illustrate this graphically, we can show the oil, propane, electric resistance heat, natural gas, and geothermal in terms of pounds per million BTUs. However, geothermal, when combined with renewably generated electricity, truly makes a zero carbon situation within reach. And whether you generate electricity on site or you buy from the green portfolio off the grid, you can truly achieve a net zero, not only in energy, but in carbon. We've developed these posters. I know you can't probably read any of the data on here. We've used these effectively to compare geothermal to other renewable technologies. And there's certainly been a debate as to whether or not geothermal is renewable. But considering 3/4 of the energy is essentially harvested solar energy from the ground. This is the first page. The second page, there's a couple lines I do want to point out in making this comparison. One is, what is the average hours per day that the various renewable technologies are available? Geothermal is around the clock, 24 hours a day. The installed cost, generally solar PV is going in for anywhere from $4 to $6 a watt right now, compared to geothermal, which is going in at about $1.50 to $3 a watt. Market penetration potential. Not every house is going to be suitable with the appropriate orientations and solar exposure to have significant market penetration. Whereas I believe geothermal, most of the buildings out there could be dealt with on a geothermal technology of one kind or another. So what do you say when your customer asks you about the environmental benefits? Keeping in mind the focus is to close the sale and sell them a geothermal system that meets their needs. Basically, I would suggest you mirror and reinforce their reasons to spend money with you. Stay in your comfort zone, but expand your comfort zone. Understand some facts that can help sway them to writing the check. So with that, I would like to move on to the main subject, the Great Hydronic Heist. I truly like this picture. That's why I put it up here. So the question, do you design or install hydronic systems using water-to-water heat pumps or geothermal heat pumps? And I know it's a growing area. A good percentage of our business is in water-to-water heat pumps, and I think there's a lot of good reasons for that. The essential schematic that virtually every manufacturer uses is a buffer tank, a water-to-water heat pump, either one or multiple heat pumps going to and from the buffer tank. And then you have your load distribution. It could be radiant, it could be fan coils, but essentially the water that's coming out of the buffer tank is going to serve your load. So the first step is understanding that the load distribution system will determine the temperature that you will need to satisfy the BTUs in the various zones of this application. Excuse me. And the use of outdoor reset or other demand-driven control strategies will allow this temperature to be optimized to improve overall seasonal performance. But using the single design day requirements will allow us to analyze the system performance. So I'm going to walk through some calculations, some examples that illustrate this point. We're going to use design day requirements. But before we proceed, let's look at distribution systems and capacities. Understanding the load. One, every application from a hydronic perspective is unique, and it must be fully understood. Experience in a specific type of application may allow some seat of the pants estimating, but should never replace the appropriate calculations when designing a system. I've seen way too many hydronic jobs get in trouble just because too many assumptions were made up front, and it's very hard to go back and retrofit and make significant changes to the distribution system. Generally, in upstate New York, and I'm sure Connecticut as well, residential heating loads will fall between 11 and 23 BTUs a square foot, with 11 being an extremely well-built, tightly constructed house, and is frankly very unusual to find builders that build that good. And the 23 being older, single-story homes. I've seen some farmhouses that might be upwards to 30 to 35 BTUs a square foot. But for the sake of our analysis, we're going to look at 18 BTUs a square foot as an overall average for a house. That's the average for a typical house, while the room-by-room calculations can also offer up a wide range. You may have a corner room with multiple windows that needs more energy in that room than a central or isolated room in the house. So let's pick that corner room, and we're going to raise it up to 20 BTUs a square foot. And we're going to say it's 280 square feet, just to give us a number to work with. So the heat loss on a design day is 5,600 BTUs an hour. To cover those really nasty days, and we've all had a bunch of them this year, I would use a safety factor for that particular zone or every zone in the house to put out more heat than the design day. Because typically with a boiler, we have a safety factor built in. We can turn up the temperature, but with geothermal, we can't. So we've got to make sure we've got enough distribution capacity to meet that load, even on the worst day you could imagine. There are several ways to deliver heat in a hydronic system. This illustrates what we call staple up. You got PEX tubing, you got heat transfer plates that help distribute the heat horizontally. The heat has to travel up through the subfloor and up through the finish floor. A typical layout from looking up from underside of the floor, you've got your floor joist. You've typically got 2 runs per floor joist cavity. Works out to be 8 inches on center. And there's a certain performance that we can then calculate with this type of setup. And that is illustrated here in this chart, where at various entering water temperatures and various resistance values reflecting what might be on top of the floor, whether it's carpeting or hardwood or ceramic, if there's throw rugs around, you're going to end up somewhere in this spectrum, with the highest output being totally unencumbered hardwood or ceramic floors. And if we put a maximum water temperature of our geothermal system at 120 degrees, then that sort of highlights the range of output that we can expect on a staple up system. Anywhere from around 9.5 to 10 BTUs a square foot, upwards to maybe 16.5 at 120 degrees with the best of floor conditions. There's another way, which is basically above the subfloor. This happens to be a ROW panel made by Rayhow, but certainly warm board, Uponor. There's a variety of above floor systems that essentially have heat transfer plates sort of built in that allow that heat to travel sideways, and then you've only got to come up through the finished floor. Much better performing. This is what the ROW panel system looks like, with the aluminum extruded plates, the PEX tubing, and typically nailer strips to give you 8 inches on center. If you remove the nailer strips, you could tighten it up to 6 inches on center. And a similar performance curve, we can now look at that 120 degree water and realize this system can go between maybe 11 to 12 BTUs a square foot to over 30 BTUs a square foot with the same water temperature. So going down and comparing ROW panel to staple up, essentially here's the output at 120 degree water with an R of 0.5. The floor area in our room is 280 square feet, so the capacity of that floor for ROW panel is 8,680 BTUs, while the staple up will only deliver 4,620. So what do we do with that when we have a desired output of 7,000? Well, we can change the water temperature. We'd like to get that 25 BTUs a square foot. For staple up, we'd have to raise that temperature up to 148. For ROW panel, we could actually turn it down to 110. Other ways to distribute heat in a hydronic system are fan coils. Typical multi-position fan coil, nominal tonnages, 2 through 5 ton. They give out pretty good heat at 120 degree water. There's also a line of fan coils, much smaller capacities. These are made by Airmec, an Italian company that have worked out extremely well with variable speed drive fans that do an excellent job at keeping noise levels extremely low and improve latent capacity and cooling. So let's take a look at a typical system, and we're going to control the buffer tank temperature, and that's what's going to cycle the heat pump on and off to maintain that tank at our desired temperature. We've got a 120 degree requirement. We figured out, yeah, that might be what's needed for this particular job. And so we're pulling off near the bottom of the tank. This happens to be a diagram from the Enertech manuals. And we're pulling off the bottom, near the bottom of the tank, feeding 120 degree water to the load. That also means we're probably coming back to the buffer tank if the flow rates are up where they should be at with about a 10 degree drop. So we're coming back into the buffer tank at 110. We're also going to be sending 120 degree water to the heat pump, forcing it to have a supply or a leaving load temperature at 130, which is penalizing the heat pump because it has to work harder to keep this tank at 120 degrees. The flow rates that we operate at are so large compared to the volume of the tank that you can virtually forget about any stratification in the tank. Another illustration, this is put out by B&D Manufacturing with their HSS buffer tank. And in this case, we've got 120 degree water that's going to go to the load. And again, we're going to have a 120 degree water go to the heat pump. 110 coming back from the load, which means our heat pump again is working to deliver 130 degrees so that we can deliver 120 to our load. A Climate Master illustration. Again, 120 degrees going to the load, 120 degrees going to the heat pump, and roughly 110 coming back to the buffer tank, and the heat pump again has to raise the temperature to 130. This diagram gets a little closer to being not as penalizing. Certainly the color illustrates a great deal of stratification, but I think it's overstating it. You might get up 2 or 3 degrees, but the flow rates we're using, we're turning over this tank every 3 to 4 minutes typically. Again, if we need 120, we've got to send 120 to the load. We're going to end up sending a 120 to the heat pumps, 110 returning from the load, and again 130 leaving the heat pump. So in spite of the fact that the industry has all embraced these concepts, the question is, why are we sending the hottest or coldest in the summertime water in the system back to the buffer tank where it is mixed and diluted to a lower temperature before we send it to the load? And what I'm going to suggest is a simple, different way of piping a hydronic geothermal system. In this case, we still need 120 degree to go to the load, but let's take the output of the heat pump and allow it to go straight to the zone with a branch circuit that will allow some of it to come back to the buffer tank. So if we need 120, we make 120. And again, our load will return at 110. and that will turn right around and go to the heat pump at 110. So we've managed to relax the stress on the compressor by 10 degrees. Now there may be times when the tank becomes satisfied, and in those situations, essentially the load distribution pump will draw directly from the top of the tank and go to the load. So we can maintain a fairly uniform delivery temperature, and then with the dead band associated with this control, the heat pump will cycle as needed. Now, why is this important? And here's a performance table of an Enertech heat pump, and all water source heat pumps pretty much have similar data. And they illustrate at a 30-degree entering water on the source side, even 40 degrees. We can look at leaving or entering load temperatures, 110, 95, and we can see the corresponding COPs. And you can tell right away that it's dramatic. We're going to do a little interpolation to pick the difference for 10 degrees, which is roughly the benefit of piping it differently. And essentially that 10-degree change will result in a 16% improvement in COP. And when we're out there competing with natural gas before the recent price hikes, you know, the geothermal may have only been 10%, 20% better. So if we were losing 16%, that is significant. I do want to recognize the real brains behind this concept. Jens Ponekau, I would encourage you all to get to know Jens. He's one of the most interesting people that I've ever met. He's decided to pick up and start Buffalo Geothermal, and in the last 5 years, they've become the dominant geothermal player in Western New York. But what I really want to recognize Jens for is not his insight, but his generosity. He freely shared this idea with me and encouraged me to go out and share it with everybody so that we can all benefit. And how about controls? How do you control these systems? Well, some important strategies. Outdoor reset. This is taken right out of a TechMar manual. The type of outdoor reset which further reduces the load temperature as the outdoor temperature gets warmer. Very important in a geothermal system. Zone demand enabled. And what I mean with that, if you don't have a call for heat from any of the zones or a call for cooling in the summertime, let the buffer tank float. Don't allow the heat pump to even run. What that does for you, it allows you to even push buffer tank sizing to be a little bit smaller, because if you do have a load that is sucking heat out of the buffer tank, it will make the heat pump think it's a bigger tank. So zone demand enabled. Velo Stratus pumps. If you're not familiar with these, I would encourage you to look at them. Certainly Grundfos has come out with a wonderful line, and they will continue to, I think, make great strides in bringing ECM technology to the market. But we've been using the Velo Stratus for at least 5 years now and have tremendous luck with it. This little device called an external off, you simply put it inside the control box of the pump, and these two terminals called external off have a jumper there. Well, you remove the jumper, put a set of dry contacts, could be on a relay, could be a bunch of zone valve end switches wired in parallel, so that if and when you get a call, you turn on the pump. Heat pumps. we typically use a boiler control. And this is how you could also disable the heat pump. If you remove this boiler demand signal, then you will not get any outputs and the heat pumps are not allowed to run. Hydronic supplemental heat. Now we incorporate 11 kW supplemental electric resistance heat, so we don't have to oversize our geothermal heat pump, but we also put it on a 3 to 6 hour delay so that we do not prematurely turn it on. Manual changeover to cooling. We strongly encourage that because you could get into days where you may need a little heat in the morning and a little cooling in the afternoon, but allow and almost force the homeowner to make that choice instead of automating it and simply going back and forth if nobody really needs that level of comfort control. Now, every hydronic job we've been involved with has presented unique wiring requirements. Now, we have gotten into the business of providing wired control boxes. This one certainly looks rather intimidating with the number of controls that are incorporated in this box. But here's the system it's controlling. 25-ton, 5-ton water-to-waters, doing 100% of the heating, cooling, domestic hot water, and a bit of snow melting. And that control box controls it all. This particular client wanted the ability to provide cooling in the middle of winter if he were entertaining in his banquet room. So we provided home run circuits to each fan coil that can come off of either the hot manifold or the chilled water manifold. The small difference in temperature. This is take again a look at the details. A heat pump capacity at 110 degree entering. This is a real life example, 49,600 with a COP of 2.61. Just by lowering that entering water by 10 degrees, we've gained some capacity, but the COP has gone up dramatically for that 16.1% increase in COP. The bottom line is it's often said that geothermal costs too much. I'm sort of the opinion that it doesn't cost enough, because if we truly do a good job, we can sell it at a higher price. And I think we are failing to maximize the value. And through simple design techniques and a fundamental competence in the design community, we can sell the technology at a competitive price and actually deliver outstanding value. And I want to close this out by saying thank you very much. And I will take it off mute and maybe get some questions. Is anybody still there, Garth?
Yes, we're still here.
Well, thank you very much.
Any questions?
We're going to go see some state legislators tomorrow, and I'd like to present this slide on the CO2 emissions from comparing coal and oil and gas to the legislators. Would you like those slides to me?
Did you hear that, John?
No, not at all, Garth. You're going to have to repeat it.
Okay. John Seaman's going to go see some Connecticut legislators tomorrow, and he'd really like to have that that slide of the graph of the different CO2 outputs of the different fuels. Is there a way that you could email that to us?
I will email the entire PowerPoint to John tonight.
Okay. There you go.
John,
My microphone's down here.
John, Pete Savino here. Thank you. You know, our members were polled and asked what we wanted to do at our dinner meeting, and we said we wanted more technical presentations like this. This was perfect tonight. It was very informative. We have so much to read, but when we hear you and watch the images, it really sinks in. I congratulate you. Thank you very much.
Well, thank you, Peter. Was it any better the second time?
Yes, it's better in Connecticut than Wisconsin.
I hope nobody's listening from Wisconsin. All right.
Anything else?
It looks like we're good, John.
Hey, thank you, every.
Presentation.
Pardon me?
Where can we go to get a copy of this presentation?
I will email it to you. You signed up online. I will send you a copy.
Thank
All right. Thanks again, everybody, and
Charge battery now.
Hey, John?
thanks again, and enjoy your evening. And behave yourself, Garth.
Absolutely. I still have to collect my free drink.
Thank you.
Thanks, John.
Yep. Good night.
Primarily, he's talking about water.